Yeah, so my name is Zane, and I'm currently a so-called GenAI architect in Manulife. Before this, prior to this, I was in tech. So I've been with Alibaba and Gojek. So yeah, so I'm actually pretty new to the insurance industry as well. But today I'm not going to talk about insurance. So don't worry, I won't sell you any insurance. So yeah, so today I'm going to focus on mostly in the complex PDFs, multimodal RAG, because actually this is a common use case, especially in financial services. We have a lot of documents that are rich in graphs, charts, diagrams, and not just text, right? So traditional RAG, right? I'm not going to read through all the text, but you can just briefly, I'll just say the problem. The problem is that. Oh, yeah. Oh, yeah, yeah. Sorry. I can see. Oh, yeah, yeah. Yes, yes. Sorry. Yeah, no worries. Is it on? I can't see myself.
Yeah, I think yeah.
Oh, okay. Oh, yeah. All right. So yeah. So the problem is that when you have like charts and graphs like this, right? It is traditional RAG will break down. Because if you're aware, maybe I'll just go through, like this kind of documents, right? A pure base kind of RAG will fail. So let me just go through how a traditional RAG can handle this. So there are a few ways to handle this kind of problem. And before I talk about multimodal RAG, which takes into account images, I'll just talk about how they handle a text. If it's just a text. So there are two phases. One is called offline and online. Offline is when you actually do the indexing, where you digitize the documents, you break it into chunks, and then you load it into a vector database. And then the online querying is when you do the retrieval. You retrieve the top case, singular chunks or documents, and then you feed it into an LLM to produce the answer, generate the response, right? So if the PDF contains any kind of image, or scan text, then usually the standard old way, traditional way of doing it is that you have OCR to detect the text, and then you have layout detection models to detect the layout, the tables, and then you try to align with the text. You extract you extract all these so-called structured information from the PDF, and you can also optionally have so-called captioning steps. When you use, let's say, a VLM model to extract the description for the image, so you have caption for the image, and then finally you feed all of them into the usual chunking indexing, and then finally you can use it for retrieval. Yeah. So besides turning everything into text, you can also use so-called multimodal embeddings, where you generate a separate image embedding. Sorry, this is the last point. Where you generate a separate image embedding using, like Clip, Siglip, or even the newer embedding models like Cohere's Embed V4 and Gina Embeddings V4. They support this kind of multimodal embeddings, meaning that what it means is that the text and the image will share the same vector space. So you can just combine, you can retrieve both of them at the retrieval time using the multimodal embeddings. Oh, sorry, so actually I should ask before this, does anyone has not heard about RAG before this talk? No, right? Everyone knows, right? Yeah, okay, so I should assume my audience is familiar with what's going on. Yeah, sorry.
What about the embedding that you do on the image there? Is it embedding on the pixels? So afterwards, in other words, you can use it to say, okay, this image contains useful context for my query. But afterwards, you still have to do OCR or?
Yeah, you mean the last one? The last
yes,
one? Yeah, the last one, you don't have to do any OCR. So you treat the image, the pixels, and you just generate embeddings out of them. Yeah, so it's how you handle text. So you tokenize the text, but for image, you tokenize the image. Yeah, and then you feed it into the embedding model. Yeah. So So yeah, so sorry. So this is very illustrative of what I just described. So maybe I should have shown this image at the start. So there are three ways to do multimodal RAG. The traditional way is the last one. Yeah, the last one is the more traditional way where you have you convert the image to text caption, and then you also you generate the text embeddings out of this description and the original text, and then you feed all of them into vector database, and then when you have a query, that comes in, you use it to retrieve both the text description as well as the original text data, and then finally you feed it into the LLM to generate the answer. So this is a pure text-based approach, and then you have the second way, which is you use text embeddings at the offline phase, but during the online phase, you can you retrieve both the image and text. So you will store both the image and text in the vector database as well. But when you generate the similarity score, it's based on the text. Okay, and then you retrieve both the image and text, and then you feed it to the multimodal LLM, like GPT-4 and above, and already can support multimodal, and then you can generate the answer. So this is still mostly text-based approach because the embeddings are still at the text layer. And then finally, you have the more modern approach which is at the top, where you have both image and text. You use a multimodal embeddings to generate the embeddings. And then in the retrieval, you also have the image and text, and then you feed it to both. So it's like a combination of different models. You can have multimodal embedding. You can also have multimodal LLM model. So you can have different combinations using these two approach, these two models to generate the final answer. Any? Okay.
How do the multi-models work together?
Work together?
Yeah.
You mean the multimodal embeddings and the multimodal LLM? Oh, usually there are two different models. So you will have a separate multimodal embedding model, which is I put here. Yeah, you can use Clip, Siglip, or Cohere's embed V4. So all these are multimodal embedding models. Yeah. And then your LLM, multimodal LLM, will be any kind of VLM, visual language models, GPT-4o, 4.1, CRAN V2.5. Yeah.
How long is the vectors from the image embedding? Are they longer than the text embedding? Yeah, when you do the embedding generation.
Of
the images, right? So what size vector comes out?
This one?
Yeah.
Oh, so if you use the same model, they will generate in the same vector space, so the dimension will be the same.
Right.
Yeah, you can truncate them, yeah, because usually nowadays they are trained using the materials. Yeah, I don't know how to pronounce, but they have this all the new embedding models that are trained using that method where you can truncate the dimension. So let's say it is like 4,000 dimension, but you want less for performance reason, you can just truncate to less dimension. Yeah.
Sorry, just now you mentioned the Clip and Cohere's method, like of the three, like how will you choose like which you use?
Oh, yeah. So they have a benchmark for that. If you cross benchmark, because nowadays they have a benchmark. So I think the state of the art is yeah. So later I will go through the meat of my content today. But the state of the art, they are based on different family of methods. If you use multimodal embeddings nowadays, it's either Gina embeddings, Cohere embed. Because OpenAI doesn't have multimodal embeddings, Gemini also have multimodal embeddings as well. Yeah, but I'm not sure what's the rank line. There's a leaderboard, maybe later I can find. But nowadays, right, the leaderboard is also dominated by the main content of my talk today, which is called lake interaction model. Okay, so when you go into the different kinds of retrieval method, Okay, so now we are at the retrieval part, the online part where you retrieve the during runtime you retrieve the documents. So there are three different dash retrieval methods. So dash retrieval is when you use a vector, you use like dash vector retrieval. You retrieve based on vectors instead of keyword search like sparse vector, right? So the first one is so-called no interaction. Okay, so this no interaction is what you are familiar with. So whatever you've done in RAG so far, right, is no interaction, meaning that you generate the embeddings separately, and then when in runtime, during query time, you generate the embeddings for the query, and then you match them using some sort of similarity, like cosine similarity, right? So that is so-called no interaction. No interaction just means that you treat them separately. So you embed query and embed the documents separately, so there's no interaction during the embeddings generation. No interaction. So this is what all the traditional conventional methods is. Okay. So, and if you're familiar with re-ranking, because after you retrieve, you can do re-ranking, right? So I think Cohere is also has a very good re-ranking model, but re-ranking is very expensive. So re-ranking is so-called full interaction, where you basically have a pairwise embedding generation. So it will take into account the interaction between the query and the chunk documents, and then it will generate the final embeddings. And then you can, not embeddings, sorry, it will generate the score, and then you can rank the score based on the descending orders. So that is how the re-ranking re-ranker works. It's so-called full interaction. And then now the main part of my talk, late interaction. Okay, so late interaction, because full interaction is very expensive. So usually you don't do full interaction at the start. You will start with no interaction. So you might retrieve, like let's say top 20 documents, and then you pass the top 20 documents into the full interaction to do re-ranking. Okay, so that is how usually you can do it. But then if you late interaction tries to balance between both. So how it works is okay. This might look scary, but actually it's very simple. Let me just jump. In the interest of time, I will jump straight to how it works. So late interaction, right? Let me see if I'm sorry. I'm trying to find the gist of it. Yeah. So late interaction, the embeddings is generated at the token level. Okay. So your embeddings usually you generate it for the whole document. So one document, one chunk. After you chunk, each chunk will have one embedding. But then, however, in your chunk, it could be very long. It could be like 1,000 tokens or something, right? So it's still very long. So late interaction, how it works is that it will generate one vector for one token. Okay, one vector for one token. So if your chunk is 1,000 tokens, you will have 1,000 vectors, for example. Okay, and then in query time, so let's say now my query is about hiking with kids. So let's say I'm trying to ask the chatbot, okay, or RAG or whatever. Okay, I want to find the articles about hiking with kids. Okay, so in no interaction, right? You will generate just one embedding for the whole query, hiking with kids, and then let's say the article is only this long one. Okay, let's assume 1 sentence. It will generate one embeddings for the article, and then one embedding, one vector for the query. So that is the no interaction style. However, in late interaction, you will have one embedding, one vector for one token. So let's assume it's a word level token. Okay. So let's assume hiking, you will have one vector, and then width, you will have one vector as well, and then kids, you will have one vector. Likewise, for family, friendly, trail dog, each of these will have one vector of their own. And then you calculate the cosine similarity between each pairwise. So you have a matrix. So you calculate similarity between hiking with family, hiking with trails. Likewise, you get a matrix. And then each of these is the, let's say, the similarity score. Okay, so you will get a pairwise similarity score between the query token and the document token. And then finally, you calculate the maximum. Okay, so you get the maximum for each query token. So let's say this row level, the max is 0.8. Okay, and then this max is 0 because there's no meaning. And then hits 0.8 again. And then you sum them. Okay? So you sum the max. You sum the max. You get a final score. So this is your link interaction score at the for each document. Okay. So I'll give you some time to. This formula essentially is about that, where you have the it's not product, so it's not precise similarity, but yeah, the concept is the same. So dot product, you dot product the vector of the query token and document token, and then you max them and then you sum them. So you get the final score is for each query and each document. Then you can rank the document based on this final score. So again, you will have one score for one document. But how you derive that score is based on pairwise interaction between the token of query and token of document. Is that clear or?
I understand, but I didn't understand how it can work because I hope the value of embeddings, right, was that it understands context. And
yes.
So when you go down to individual token, there's no more context. So that's where I'm stuck.
Right. Yeah. So if you think about it, right, the beauty of no interaction, meaning the usual embeddings, right, is that it, like you said, like it condenses the information, but sometimes it over-condenses the information. So let's say if like I said, if your chunk is very long, you might lose, it's a lossy compression, right? You lose some information within that chunk, right? So when you do the retrieval, it might not be perfect, However, if you do it at a token level, yes, it might seem overkill and very expensive. However, you get richer interaction because if you think about it, right, how the re-ranking works, why people use re-ranking, this full interaction, which is the usual re-ranking, is that they will generate one final score between the pairwise of query and document. So that's what we are doing here as well. We are basically doing something similar like re-ranking, like a full interaction. However, we have some shortcut, so it's not like the full interaction stuff. So our shortcut is when we still generate the embeddings. We can pre-generate the embeddings for the document. We cannot pre-generate for query because we don't know what's the query going to be. But for documents, we can generate the embedding first, and then in runtime, we just have to generate embeddings for query, and then we can calculate this, which is very cheap. Because for full interaction, you cannot do that. Full interaction, it depends on the query. So you cannot do any kind of preparation. So every time a new query comes in, you have to run this whole thing. Imagine it's like a bird kind of a model, then it will be very expensive and it's going to be very slow. So that's why usually people don't do re-ranking on their whole suite of documents. Yeah.
Sorry.
Yeah.
In a actual like industrial or commercial scenario, like how often do you actually run rack?
Rack. Oh,
How
actually.
often do you actually run like like the re-rankings?
Oh, re-ranking. Re-ranking is more expensive, like I said. So usually we will do it if it's necessary. So let's say if the performance is not good, like the regular retrieval is not good, then you will feed it into a re-ranking to re-rank again. Yeah.
And then how do you define like not good? Like is there a certain benchmark that you use?
Oh yeah. Like I think it's out of scope, but usually we just use that standard like Raga's kind of metrics. Yeah. There's a library called Ragas where there are a lot of libraries, but one of them is called Ragas, where you can calculate the retrieval score. Yeah. Context precision, context recall, all this. Yeah. So you can evaluate. Basically, the point is that you can evaluate and then you can decide what is the method that you want to go more advanced or go simpler. Yeah. Okay. So yeah, so maybe I'll get to that point when you look at the image, it will make more sense. Okay, it will make more sense once we reach the image part. Because so far what I've described is just text, right? We still haven't reached the image part. So for text, it's called Colbert or Kobe. Yeah. So it's basically the original paper that came up with this link interaction method, but it only works for text. Only works for text. So when it comes to image, now how it works is that they will feed another they will feed another VLM to generate the embeddings for the image. And how it works is that, yeah, here. So here you have the document. You treat one document as an image. One page as an image. So one page, you can break it down. You can tokenize the image by breaking them into patches. So let's say they have, let's say 4, for example. You have 4 tokens, so-called tokens, and then each token you can generate embeddings. So you have 4 embedding, 4 vectors. Okay, and then in runtime, so let's say the runtime tree is a text, right? During query time, you still ask them to type with text. Of course, you can use image as well, but let's say it's text. You have 3 vectors because it's at the token level. So 3 tokens, 3 vectors. Here we have 4 tokens, so 4 vectors, and then you do the max thing, and then you will get a final score. Oh yeah, sorry. Okay. So so if you think about it, it might make sense for image, right? Because if you try to condense one whole page with just one vector, it might lose some information. Okay. So if you break down the page into multiple patches of image, and then you run the maxim that I described just now, then you can maybe you have more richer information that you can capture in the retrieval when you do the retrieval. So this is called ColPali. So it's named doesn't say the coding, but they use the PaliGemma model as the first one. The first one is PaliGemma to do this, and then so this is how it works now. So like let's say you have query is text. You go to Gemma, and then for the image, for the offline indexing part, you go through PaliGemma, and then you can pre-calculate this because this can be done offline. So you can calculate this offline, and then online you feed a query, you do the maxim, and then you calculate the sum. Okay, so this is how you calculate the score for ColPali. And then you have CRAN 2 and CRAN 2.5 came out with the VL, the vision language. Vision language model. So then they also have CoCRAN. Okay, and then the state of the art nowadays is called ColNomic. Okay, which is what I'm going to demonstrate today. ColNomic. So it's still based on CRAN 2.5 VL, but they continue train on top of it. So yeah, before I move on, is there any questions about this?
The size of the patches, what is it typical?
Yeah, I think it's somewhere, I can't remember. The max 768 patch size, meaning it's sorry, I think it's mentioned somewhere. It's hidden in the whole text of words. Yeah. 128 okay, I can't remember where it's where I put it, but 128 dimension embedding, this is the dimension size, but the 768 is the patch size. So it's like I don't know how many times, sorry. The square root of this. The square root of this one. Yeah, it's the square root of this. Yeah. So but different architecture have different patch size. So ColPali has a different one. ColCRAN, I think it's 28, if I'm not wrong. Is it? 8? Oh yeah, a bit off, but can't remember the exact match, the patch size. Oh, is it not square? Oh, it should be square. It should be square. Yeah. So
So on a normal page, it's like the size of on an A4 page, it's like the size of the postage stamp. So is your diagram like cut into 4, right?
Yeah.
So in reality, you cut into many more pieces.
Yeah, many more.
Yeah.
Yeah, so it would be like smaller. Yeah. So yeah, it will be small enough. The point is that it will be small enough. Yeah. So okay, I think enough talking. Maybe I'll just show you a bit of at the code level. So you can actually run this in pure just overweight models. So you don't have to call any API because nowadays this ColNomic, I forgot to mention. So this state-of-the-art ColNomic is open-weight models. So I think it's Apache 2 license, if I'm not wrong. So it's completely you can use it for commercial as well. So the VLM, you can also use commercial. You can also use open-weight models. Like the most recent one is the Mini CPM V4.5 and Intel VR V3.5. So these are like the current state of the art for open-weight VLM models. So how we're gonna do it is this. First, we're gonna retrieve using the ColNomic multimodal lake interaction. Okay, so you retrieve the relevant pages, and then you still have to feed into a VLM to generate the final answer. Okay, because ColNomic is just for retrieval; it doesn't give you the final answer. Okay, so this is the flow, the workflow. So yeah, I think it's sometimes cutting off. Now I don't think it's a mic, maybe the signal. So okay, so yeah, you just have to install. Actually, all these are the standard libraries like transformers. If you want quantization, you can install bits and bytes. And all these new models need flash attention tool. So you need to use Ampere architecture and above the GPU, because if you use like the free collab one, it doesn't support flash attention tool, so you can't use this kind of model unless you use the paid collab, which is A100, like this. So then you can use this. So that's why I'm using this this model platform. So we're going to use this PDF, which is the state of the Southeast Asia. Which has a lot of tables and tables still okay, but they also have diagrams. Okay, so a lot of tables and diagrams like this, and we're gonna do an example. So let's say, I'm gonna skip this now. But basically, this is just loading, downloading the file, the PDF file. Yeah, so you can see here all the PDF images are here, about 70 over pages, and then you just have to load this ColNomic. Like I said, it's open-weight model, 7B parameters, and then you can index it. So this is when you do the preparation, you index all 70 over pages of the documents. And in production setting, usually you will want to feed it into vector database, because nowadays, all the commercial database support multi-vector embeddings. So you can use any of this to index your vectors. But now I'm not using any of this. I'm just storing it in a file, in the index file. And then for your VLM, you can use any kind of VLM like Mini CPM or this InterVL, which is just any kind of visual language model will do. So how it works is that in runtime, you can pass any kind of query. So let's say which ASEAN country was the top holiday destination for Singapore respondents or Singaporeans, right? So when you do this, you just have to do a search. You can search top K. Here I just put one up. So let's say I only want to retrieve one page, okay, because it's at the page level. One document is one page. So I retrieve one page, and then this is the page that is retrieved. So you can see it's the correct page. So ColNomic, this is the ColNomic model. The ColNomic model is able to retrieve the relevant page out of the 78 pages. It retrieved the relevant page that is pertaining this query, okay, which is the holiday destination. But you might say, okay, it's easy now because the title already has holiday destination. Yeah. So later I'll show you a more complicated example. So once you have this image, you can feed it into yeah, sorry, this one I need to rerun because this one is a bit outdated because I was running something else just now, so the response is a bit off. So you can see it's streaming now. Okay, sorry now up here. Okay, so was Thailand with 33.7% of vote, but actually this answer is wrong because this is they are just taking this 33.7%, but actually Singapore, you have to look at the row, and the most popular is actually Malaysia at 34.5%. Okay, so Thailand is actually 31%, so it's the second highest. So they only take for the whole ASEAN. So these three numbers are the whole ASEAN. So it's a wrong answer lah. So if you plot this if you plot the answer together with the image, you can see that it is a wrong answer because it quotes Thailand, okay, which is wrong. So let's see if we can use thinking mode. Thinking mode is a bit okay now. Sometimes it works. When it works, it's good. Sometimes if it doesn't work, it's a bit yeah, it just go round and round in circles lah. So yeah, so wait, keep waiting, right? And then keep thinking about it, and then let's see if it works out. So like one or two out of five times it works. So it depends. So sometimes it works, sometimes it doesn't. Okay, yeah, now let's look at the table, right? It says, okay, let's try to look at the table. But sometimes when they pass the table, the values is also wrong. I don't know whether it's because the resolution issue, they are not able to see the numbers clearly. But finally, sometimes it will give you still the wrong answer, but let's wait for it. Okay. The correct answer should be Malaysia. So Malaysia should be the top. According to the table, it should be the top. Yeah, actually, he already has the answer, but he keeps thinking again, like go around in circles. Yay! Correct. Okay, yeah, it works. Yeah, you saw. Yeah, that's why we're lucky, I guess, because I think like 40% success rate usually. So if you use Intern VL, it's supposedly a stronger model, but I don't know, sometimes the answer also, oh yeah, it works also. Yeah. So Intern VL is 38B, so it's a bigger model, so it should be more powerful. It should work. So just now the one that I used, the thinking mode is mini CPM, but both of them have thinking mode. So Intern VL, you can also prompt it to do thinking if you want. Okay, so yeah, so let me just show you another example before I think time is almost up. So let's say this is actually quite simple, but you need to do calculation. So how much percentage is made up by the top two options to respond to rising protectionism and nationalism in ASEAN? So again, the image is correct. Okay, later I'll show you the image. Yeah. So if you see here, this PDF is correct. So ColNomic, again, as usual, it can retrieve the correct image. And then how about the answer? The answer is 40.2 plus 30.9, 71.1. Because you need to reference this pie chart. So the pie chart, the top two is 40.2 plus 30.9. Yeah. So you need to reference the pie chart and then you need to plus both the numbers together. So it's correct. Okay. And then let's look at a more. So yeah, so this one is a bit more tricky because you need multiple pages. Because I asked it to summarize the perception of each country of China. So if you look at the original report, it's all over the place. Like you have 2 pages here and then 3 pages at the back about China. Because I mean, yeah, it's a huge topic, right? So I retrieved 5 because all along I only retrieved 1 page. It's able to answer the question. But for this, let's say if I retrieve 5, will it work? So Yeah, so you try to give me a summary of each country about their perception of China or the trust of China, and oh yeah, so it's just doing some summarization. So the answer actually depends because there's no right or wrong. The answer could be about how you perceive the data, right? So there's no right or wrong for this, but this one you have to look at the report to really ascertain the accuracy of this answer. Growing skepticism. So yeah, the answer is actually wrong because when I look at the report, 2025, the trust in China actually increased a bit, yeah, compared to 2024. So I think this answer is wrong, but again, this is a complex example, so you probably have to tune the retrieval and the VLM to the prompt as well. So yeah, so actually that's all for my part. Any question?
It sounds like the RAG worked very well to identify the relevant pages.
Yeah.
And just the RAG factor got the wrong answers because the VLM, at the end is not powerful enough.
Yeah, because we are using relatively small, even the largest one is 38B, but if you use like Gemini or whatever 4.1, GPT 4.1, definitely you will nail it because you really have the right image, right? Yeah.
You mentioned that some of this requires flash attention and that does work on the base Google Colab GPU. What's like the minimum spec for a GPU to run flash attention? Does it need to be an A100 or?
Yeah. So the GPU, if you use T4, definitely it won't work. Flash attention tool, yeah, flash attention tool won't work. So you need at least like L4 and above. So the L's or the A series, yeah, or H, yeah. If you are rich, if you have H, you can also use H, yeah. So yeah, so that's one thing. Another thing is the memory. So if you use T4, 16 gig, it won't be enough for even like a 7B. 7B usually, if you don't quantize it, it won't be enough. So you either need to quantize it or you need to use a even smaller model. Yeah. Oops. Yeah. So I think that's all for my part. If you still have questions, you can ask me after the